So this is Computer Science 305, Programming Languages, and again we're talking about, this is the continuation of the Syntax meets Semantics section. And so we had just gotten done, we walked through operators, precedence, associativity, and other ambiguities. So basically we have talked about how do we address certain ambiguities, and how also do we address different levels of precedence as well as different types of associativity. So now, we just got done talking about how we handled the dangling else problem, and so now we're going to move on to the cluttered grammars issue. So now, the new if then else grammar that we looked at, we identified would be harder for people to read than the old one. And we also note that it has a lot of clutter going on. It has extra productions, a whole bunch of more non-terminals, and we can actually argue that in the previous grammars G4, 5, and 6, we eliminated ambiguity but made the grammar harder for people to read. The question becomes, is this the right trade-off, right? Every time we make a change, improve the grammar, we add new things, it makes it hard to understand. So one needs to strive for the right balance in this. And so we talk about, way back when we were first talking about grammars, that there are multiple audiences for what we're looking at, right? And so, we have novices who they just want to understand how to actually program in the language. So what actual valid programs would look like. Experts and tools, on the other hand, need the most advanced form of the language, right? They need to be able to see what the exact detailed definition of the language is, in order so that they can develop the tools. The tools themselves have to create the actual parse trees and abstract syntax trees in order to actually handle and parse a language into a parse tree and be able to convert that to machine code as necessary. So tools are those which require the ambiguity to be eliminated, while people actually prefer the more readable grammars, right? The initial grammars prior to us fixing the ambiguity. So we have a couple options, right? We can either rewrite the grammar and eliminate the ambiguity, or we can leave in the ambiguity but explain in other text attached to this, right, how things like associativity, precedence, and dangling else should be handled. Or you can do both, but in two separate grammars, right? So you have one that is for the tools to use and one for the people to read. This moves us towards parse trees and the EBNF, right? The EBNF, which we've already seen, is really slick and adds these extra capabilities so that we can make the grammar a little more efficient. And so, but unfortunately though, we do know that there are some issues with this, right? We know that if we use curly braces around like X, that means 0 more repetitions of X. And so if we were to write the rule, if we go back to our multiplication, right, and we said, well, an expression could be a multiplication expression or a multiplication expression plus a multiplication expression. Really what that's saying is, what this thing is actually saying here is that's not what we want. We rather see is it's multiplication followed by 0 or more, not 0 or 1, plus multiplication expression, right? And that's not necessarily what we want. Because this actually leads to issues with the associativity of this specific expression. So in order to deal with associativity in EBNF, right, we need to probably, there's like a couple approaches, right? The first approach is the simplest, which is we just use the curly braces for repetition wherever we need them, and then we just add an accompanying text that describes how to deal with any ambiguities or associativity that we need to handle. On the other hand, we can define an actual convention, okay? For example, the one that we showed could only be used for left associative operators, whereas we use explicitly recursive rules for anything unconventional. For example, the one below is the right associative approach for handling which has a right recursion for handling assignment, right? That's the assignment operation. So these are two different approaches, right? And then we can shift to syntax diagrams, right? Remember, looking at these, they have a similar problem, right? What parse tree would be generated? For these specifically, you can just add a paragraph of text, right, to describe how to deal with all these problems, mainly because at this time, I haven't really heard of anything that can process a syntax diagram and turn that into a useful scanner or parser. So we're not too worried about tools or for experts using these as a way to define the actual tools they need to build. So that gives us that. The next topic is actually very important. It's the abstract syntax tree. And so we have to think about, first off, what does a full-sized grammar look like, right? So far, we've looked at really small, tiny grammars that fit on a slide. And in reality, we have, like, if you want to build a grammar for a language like C, these things are huge, right? They're very, very detailed, a large number of non-terminals, large number of terminals, actually. And the problem here is that it becomes extremely cluttered, right, to when we want to create the unambiguous form. And that's mainly due to the creation of extra non-terminals that guide the construction of the unique parse tree. But once that parse tree is found, these extra non-terminals essentially have no more interest or use. And that's sort of how we get into this abstract syntax tree, right? So when we look at these languages, right, they normally are stored in an abbreviated form of parse tree, right? This abbreviated form called the abstract syntax tree, and it's and the details of its abstract syntax tree is typically called an AST. So the details for an AST are implementation dependent, right? It's dependent on whoever's building the tools to actually do the compiling or the parsing. But we do know that oftentimes there is typically a node for every individual operation, as well as and then for that operation, there's an individual subtree for each operand to it, right? And so essentially, if we look at our parse tree, right, is the much more verbose, showing us all the individual non-terminals. But in reality, we don't need that much information. We just need an abstract syntax tree that can handle it, right? So we see the actual plus sign. It's broken down to another plus on its left, which is then broken down into two terminal nodes, A plus B, so A and B, so we can process that as A plus B. We then add that to the right side of the root terminal, the root node, which is the plus, and we see that there's a terminal there, C. So the abstract syntax tree is a much more reduced looking version of this. Basically, we can just take the terminals and shift them up to their closest node, and that's what's been done. So if we want to take a look at this, right, basically the whole point of this entire process, understanding all these grammars and everything, is to get us to the point where we understand parsing. And basically, when a language system parses a program, it goes through all the steps necessary to find the parse tree, but usually does not constrict so we do have to understand that it's going towards trying to figure out the parse tree, but in reality, holding a parse tree in memory would not be very efficient, and so most of the systems just construct an abstract syntax tree instead, and because it reduces the amount of in-memory data storage. And so we'll come back to that near the end. I may spend some time on that or not, but if we do, on the other hand, you can always go ahead and read that section if you want. In conclusion, our grammars not only define syntax, they also define the parse trees, which is what defines semantics of the program. So that's the concept, right? A grammar is not only what is legally usable in the system, but also what is the parse tree. The structured parse tree is the order in which things are executed. Thus, it's the definition of semantics. So therefore, so now we've connected everything we've done so far up to this class, we've looked at the history of programming languages, grammars, different ways of defining grammar, and now we've shifted into syntax and semantics, and now we really understand how all this stuff is kind of coming together to where we can start designing languages. Now what we need to understand is, now we know how the grammars are actually developed, we need to have an understanding of types, type systems, and now we get back in connecting ourselves to the underlying mathematical theory of programming. And so I leave that for the next major lecture.